Okay, first up, we have Gerwin Klein, Chief Scientist of Proofcraft, instigator of the verification project. He's going to tell us how to solve the problem that Gage mentioned before, that it's too hard, that there aren't enough verified platforms. Thank you, Gerwin.
Yeah, thank you very much. It took away all my thunder. I was going to thank Gabe for the brilliant setup for this talk. That's one of the problems we will be trying to solve. So reducing the reliance on verification experts for seL4 proofs is the overall theme. And it's all about making ourselves redundant or obsolete, but only for the boring parts. We still want to be here for the interesting parts. Great. Good. I'm sure you know the saying, faster, better, cheaper, pick any two of them. Sometimes it is enough to just pick two. So if you think about this a little bit, when you have proofs and you manage to keep the proofs intact, but you make them faster and cheaper, well, overall you have better. So, you know, those are the two to pick, faster and cheaper. And overall, you're going to have a better product. So how do we do that, and where do we have opportunity for this? Well, we heard formal verification is great, but there are two main bottlenecks. One is the availability of experts. There's actually more and more formal methods experts out there, but people like, AWS and Apple and so on tend to hire them, and so they don't work on seL4 anymore. Good for them, but it's still a bottleneck for us. And then even if you had 600 instead of 6 proof engineers in Proofcraft, you would still not be able to scale everything to the degree of 100 times. Because formal verification as such is not so easy to scale, especially in terms of development time. You can, if you set it up just right, then it can work, then it can scale linearly, but usually it doesn't. So what can we do? We can improve little bits of that. So one thing we definitely want to improve and decrease is the proof maintenance cost. So right now, we're supporting 4 architectures, soon 5. And whenever we do a change that affects multiple architectures, we have to do that change in the proof 5 times. That's a little bit sad. So, the more we can do to reduce that to 1 time, the better. So that'll save a lot of cost. And it will also mean that we can move faster because, we have to do less work. The same kind of thing will help to increase proof development speed. So making the proofs more generic, more agile, that's sort of the theme. And very specifically, there is one kind of task that is kind of boring that we think we can fully automate. And this is the verification of platform ports. So that's the real title of the talk, basically. And as you've heard, there's a lot of unverified platforms. Actually, in 2 talks now, that was a topic. So what is the situation like? If you look at architectures, we actually have a pretty good spread of support. We have ARM32, RISC-V, 64-bit, x86, and we will pretty soon have at least functional correctness for ARM for AH64 as well, to be finished in March, and that is looking very good. That's completely on track. But at least in the old days, i.e. last year, we supported exactly 1 board per architecture. So, that's not a lot. And there's reasons for that, going further back than 1 year. Very recently, i.e. this year and last year, we've extended this a little bit. So there are now 3 supported boards for the ARM 32-bit architecture. If you're interested, it's the Saberlight Exynos 5 and the IMX8MM EVK. But the way this has to be done right now still is, well, it's kind of iffy. So you basically make a Git branch which duplicates the proof. You do all the changes you need for that platform port, and then you have to maintain those branches. We developed some automation for that for the seL4 Foundation, and that works. So As long as you make changes that are completely orthogonal to the platform port, it will be automatically updated, tested, and so on, and will be up to date. That's cool. But A, they all have to be tested, and B, they're not going to remain orthogonal if I do, 50 boards instead of 3. So the way we've done those is not scalable. And so what kind of scale are we talking about? Right now, seL4 supports 32 different platforms, which is actually kind of cool for, a little open source microkernel, or not so little. But only 6 of these support verification. That's 19%. That's also not terrible, but it's it's not awesome. And what I would like it to be is, well, verified everywhere, right? Even if you can't do everything, just 90% would be pretty great already. I think we can actually do everything in terms of which boards, but maybe not all features of all boards. So specifically, system MMU, for instance, that's not just a little board feature, that's a whole new proof. But I don't know, BeagleBone Black versus Saberlight, that's not a huge difference. So both should be able to be supported. Thinking a bit further, not just those 32 platforms, but assume you have your own project and you have your own new hardware platform that you need to use for some reason. It's not in the officially supported list, but there's a porting guide out there and you can go and port seL4 to your platform. And if you follow the instructions and you're lucky, it'll work. So that's cool. But now, well, you need a proof update. If you rerun the proof, chances are extremely high the proof is going to say, no, this is not what I expect. You changed something, fail. That's still not so bad. You can contact us, for instance. And we can look at that. And usually these things are not so hard, right? Effort is between a few days and a few weeks. Unless, it's a big new feature like a system MMU or something. So that's cool. We'll do that for you, and we'll do the proof update. We'll add another branch. Everything's cool. For your part, you're done. For us, well, the proof test combinations multiply. Everything is, times one more. Maintenance cost increases even more. So next time somebody comes along and needs a proof update, well, we're going to have to charge a little more because it's going to take us longer. And if you do that 50 more times, that's not really sustainable. I mean, maybe from a business school perspective, that's exactly what we should be doing. But I didn't go to business school. I did computer science. I want to get rid of that stuff. So I failed business school. No, I didn't even go. So, okay. So technically, what's happening here is the update as such is relatively easy, as I said. The maintaining multiple proof versions is pretty painful. So running a proof for one version, for one board, takes about 6 hours for a single proof check. Well, you add another one, it's 12. Add another one, it's 18, and and so on. You can run them in parallel. But there's still a limit to how many AWS instances you are willing to pay for one proof run. Last time I requested an upgrade in the number of available vCPUs for seL4 testing. AWS just replied denied. And I had to request a smaller number. So yeah, and that's just in the good case, right? If you made a change, you tested it, it worked. If you made a change and something breaks, now you have to go through all of these and figure out, did they break for the same reason? Do I need to make the same change, and so on and so forth? So definitely not scalable, maintainable, and so on. And these are boring things to do. Like, we got into proofs and proof engineering because we like the interesting things, not the boring things. So we are highly motivated to eliminate that stuff completely if we can. And that's the plan. Okay, so the ideal future would look like this. You still follow the porting instructions. Maybe in the ideal future, they're so great that, it takes you absolutely no time. And it'll all work. So that's good. Step 2 is the seL4 build will automatically check the necessary conditions for the new values you put in your platform ports and so on. And it will generate a configuration file for the proofs that the proofs take as input. And when those checks have succeeded, you should be able to know that this config file will succeed with the proof. You don't even need to run it, really. If you want to be extra sure, provide the config file and rerun the proof. But ideally, it should be set up so that this is not even really necessary. And that's it. Come on, the end. There's a lag between this and this. So notable omissions in this thing. You didn't have to contact us. You didn't need any proof engineers. You didn't have to pay any money. And we didn't have to add any Git branches to the bloody proof repository. So this is what we want. We'll see how achievable this is. And there's no guarantee this will always work, right? These checks might fail, and they might fail for the reason that, okay, the values were wrong and you needed better values. Or they might fail for the reason that the values actually work, but the reason they work is a new reason, and the proofs don't know about them. Or we didn't, or our sufficient conditions were not tight enough, basically. They were too lax or something like that. Okay. So in those cases, you should still contact us. But those are the interesting cases. Those we like to do. Okay. So why do we think we can automate some of these, and maybe a little bit of how? So this is on the slightly more technical side. So what changes when I do a platform port for seL4? There are two sets of things that change. I call them platform parameters and config parameters. Platform parameters are really the things that are specific to a new board, and config parameters are actually more specific to your project, but you might set default values for a specific board. You don't have to read the blurry text in the background, but I'll talk about what they are. So on here, there's one of these device tree overlay files. That's usually where you give things like, this device is at this memory location. The board has memory going from A to B. The timer driver is over here, and so on. This here is a CMake config file for the platform that declares, what is its name, does it have an FPU, and so on and so forth. So the platform parameters would usually be actually set in both, in a mixture of both, but mostly in the device tree file. It says specific numbers for where devices are, where memory regions are. And then the other stuff is usually in the CMake file that says, do I have an FPU? What kind of IRQ controller does it have? Is it a hypervisor board? Does it have a system MMU? And so on and so forth. So that's one. The config parameters are more, is MCS on or off? Have I switched on the fast path? How many domains is the project using? What's the size of the initial C node and stuff like that? And, well, if I stare at these things long enough, some of these look like obvious candidates for automation. So the memory regions, for instance, they're just a bunch of numbers. Surely we can, if they're different numbers and they're good numbers, surely we can do something there. I'll talk a little bit about how exactly, but they're good candidates. Then here are some that are a bit harder. So FPU, IRQ controller, and so on. Even the number of domains, that's just a number, but if you look at the code for a little bit, there's a big difference between number of domains 1 and any other number of domains. 1 means there is no domain scheduler configured in the code, and anything from 2 to 255 means there is a domain scheduler and it uses that number of domains. And that selects different code. And that means the proof has to deal with different code. So you would have to have one proof that can deal with two kinds of code. Specifically for the number of domains, we actually had a little project where Raf made it so that you can plug in any number of domains, even one, and the existing proofs will work. So that's quite nice, and that is one of the pre-projects that gave us a little bit of confidence that this might work. The other ones, they all have in common that they select different parts of the kernel to be on and off, basically. So similar to this number of domains thing, if you have an FPU, the size of some kernel objects changes, you have some additional code paths and so on and so forth. You want one proof that can deal with both cases, if you want that genericity. And then there's some config parameters and platform parameters that are a little bit harder. In a sense, they're quite similar to the ones I was just talking about, but they're just bigger. So is the kernel a hypervisor or is it not a hypervisor? That's quite a big difference, and they're really just different architectures in the proof in the end. Similarly, is MCS on or off? Those are two pretty much different kernels in the end. So we're not going to try and make one proof that is generic on that. We're going to keep combinations of hypervisor, MCS, and so on. Although MCS, in the future, when we have it, we actually want to make that just the default, and it'll be the MCS kernel, and we'll phase out the other kernel. And maybe I won't be retired yet when that happens. I don't know. Hopefully not. Okay, so there's a plan for those, but it's a different plan. So they will not be proof generic in that sense. Okay, so the easy bits. Let's go back to those, because those I can explain. Why does the proof even break for those? Okay. Currently, how it works is that in the specification, there are fixed values for these things. So somebody from the formal side sat down, looked at the manuals, said, okay, the load address for this board should be blah. They probably talked to the kernel people and said, hey, we're using that load address, and we put in that number. But yeah, we look independently basically at the manuals and arrive at the same numbers. Usually with a little bit of iteration, because one of us is wrong, and it's usually us. Because if you think about it, the implementers, they're probably also wrong the first few times, but they tried it and it didn't work. They kept going until it worked. And let's call that process validation. Anyway, those numbers are in the spec. And if the proof finds a different number in the code, then, well, it fails. That's what it's for, right? If something unexpected happens in the code, then it should fail. So that's reasonably easy to think about. So step one, what we could do is, let's get a single source of truth for what those numbers should be. And since the code, in this case, happens to be right much more often than the spec, our proposal would be to generate those values for the proof, for the specification, from the cconfig. And if you think back to the beginning of how this worked, there was exactly one board, and it made a lot of sense that a bunch of people were sitting down, validating those numbers in one team, and then doing it again in another team. Those numbers were also sprinkled throughout the code. seL4 has evolved quite a bit from that. So all these config files that I was showing you, they didn't exist back then. So they're now actually nicely collected in relatively few places, and they're a good source for validation. So first of all, it's in one place, so you can find them. Second, you will notice when they don't work, because you're trying to get the thing to boot. And chances are pretty high that if you say your timer driver is here and it works, then it is actually here. So the validation process on the kernel side is the better validation process. So we want to keep that one. In terms of assurance and evaluation, those are things you probably want to double check though. These are not things that the proof will give you any assurance about. Okay, and then the naive way of doing it would be you go through the proof and you see wherever it mentions the number, I don't know, 17 for the load address. You remove 17 and any mention of the number, and you just use the symbolic value load address. And whenever it has to do some computation on it, you just unfold it and hope that automation will deal with it. And that actually works. I was going to say, well, the first step of how we did the num domains thing worked like that, and that's okay. But that does actually not yet really solve the problem. I mean, it will solve the problem in the sense that you put in a different number, the same automation will still probably prove the property you want, but you still have to rerun the proofs every time, just to know if it will work or not. So you're not saving on the explosion of combinations and branches and so on. What I just said. So that's not sufficient. What we can do instead or what we should do instead, is properly parameterize the proof. So instead of just using a symbolic value and unfolding it when I need to know something about it, I need to go through the proof and figure out what is it actually that it needs to know right now. Is it trying to prove that the number is greater than 0, or that it's smaller than some other thing, or that it's aligned to some specific size, or that, I don't know, the kernel boot address is not within the addresses available to the user, for instance, properties like that. And then instead of just doing that in place, I extract that as a property, as a lemma. I collect all these in one place. And then I never use the actual numbers in the proof. I only use those properties. So if I have changed the proof like that, then I will have a parametric proof in the sense that it'll work for any number that satisfies the properties. And to check that proof, I don't even need to rerun the entire proof. I have a conditional theorem in the end. Like, if those properties are true, the kernel will work. So I just need to satisfy the first if those properties are true. And I can do that in a small separate file that also doesn't have huge dependencies and doesn't need 6 hours. And what is more, those properties are pretty simple things. They're like, A is bigger than B, X is aligned to something. I can write a dodgy Python script that checks that. And if the Python script says yes, then my probability that the proofs will say yes is very, very high. And that's sort of the build check step. That's the plan. So we haven't done that yet. That's a future project, but such is the plan. So what about, one single proof that works with and without FPU? Well, Raf says, I don't promise that yet to people. My answer is, okay, I won't promise it. But I do have a bunch of ideas, and I think at least one of them might work. So we will give it a shot. I don't want to bore you with the details of exactly how I think it should work, but I think there's a reasonable chance of success. That's more a research project than this is the plan we will follow. Okay, so remembering back, the goal was follow instructions, build automatically, check stuff, and you're done. And if you want to be really sure, you rerun the proof, and you don't need to maintain any branches and things. We think that is quite achievable. So there might be cases where we don't quite cover all the combinations and so on, but we'll definitely be working on that project. All right, when can you have that? Well, it's not the only thing we're working on. There's a whole bunch of things. So I mentioned the AH64 verification. That is hopefully soon completed. There is MCS verification that is ongoing. It'll be, I don't know, I hope, no, I'm not going to make any promises, but 2024, maybe for RISC-V. And then sometime after for AH64. And that switch from RISC-V to AH64, for instance, is one of the things where we want to make the proofs much more agile. So we will actually be working on making that agility happen first, and then switch to AH64, and maybe to ARM and x64, and whatever else there is by that time. Multi-kernel verification is now ongoing. It's, it's a small project right now. We're looking for further funding, and, well, with a bit of luck, we might get some. And then there is the Agile Proof project. Funding for that is, I would say, very likely. It's, nobody has signed on the dotted line yet, but you can see the dotted line in the in the distance. And if everything works well, this will be starting in 2024. And so that Agile Proof project includes two things: the platform proof automation that I was talking about, and more agility and more generic proofs in general. So, for instance, switching between architectures should be much simpler in the future. All right. So, in the future, we should have platform ports, no experts required. Proof maintenance, faster and cheaper, which, in total makes the proofs better. And proof engineers should be much happier and less of a bottleneck. What that means for everybody else is that we have more capacity for interesting features and updates, so we can do cooler stuff with the proofs. All right, thank you.
Any questions? Yeah, Gerwin.
So how will this automation be affected if and when we have verification of the kernel initialization?
To repeat the question for the recording, how will this automation be affected if and when we have proofs for kernel initialization? There will be more properties that are generated from that, I think, but I don't think any fundamentally different ones. So I think the same approach will work, but yeah, it'll take work to integrate it.
Any more questions? Oh, Gage.
Hopefully just a quick one. So if I understand this correctly, you've got these platform-dependent constants and you're trying to prove something about a general set of them as opposed to them each time. Can anything bad happen if the proofs are checked out, but you've got the wrong constant for the platform? I mean, from a security perspective, beyond the fact that it's not booting, could it boot, run, but somehow it's got a problem?
Probably yes, in the sense that, well, I struggle to find anything, but my default answer would be, yeah, you want to double check those numbers. Let's say you confuse two devices and one of the devices isn't used for a long time, and you will not immediately see the effect after boot, for instance. That might be one thing. I don't think that actually happens because the timer is used pretty much immediately, and IAQs are also pretty much used immediately. So probably a fairly low degree of probability there, but I wouldn't say, yeah, it's definitely going to be fine. Don't even look here. I would double check those numbers.
Maybe one more.
It's not really a question, but
More of a
how
comment.
do we make this happen faster?
You can give us the money now instead of waiting for the funding. Then we could start right now instead of 2024. You could no, I don't think that is in anybody's power. Make the negotiations for that contract go faster.
Is the question of more money for Proofcraft to prioritize that?
Yeah, I think so. I mean, we need to deliver the AR64 project, and that right now is staggered pretty nicely with the start of this new project. I mean, we could hire more people to do the work in parallel, but that's pretty much it, I think. You will get it. It'll be there.
Cool. Let's thank Gerwin.